Testing. Okay, so today's lesson is going to be on an introduction to gas laws, and we're going to do this through the use of what I call the PVTn chart. So let's look at example number 1. We have a sample of gas, and it has a volume of 180 and a pressure of 740. We want to know what volume of the gas will occupy the pressure if the pressure is increased at a constant temperature. So temperature is constant, and N stands for moles of gas. That's not changing. So we're looking at the relationship between pressure and volume. This relationship is Boyle's law, B-O-Y-L-E'(S), Boyle's law. And Boyle's law says that pressure and volume are an inverse relationship, meaning if pressure goes up, volume goes down. If pressure goes down, volume goes up. So inverse being opposite. So to do our PVTn chart, our initial volume is 180. And our initial pressure is 740. Now, what volume will the gas occupy if the pressure is increased? So our new pressure is going to be 800. My pressure went from 740 to 800, so the effect is an increase in pressure. And if it's an inverse relationship with volume, that means volume will decrease. So, to set this up, my volume started at 180 milliliters. Now, I want to know what is the new volume. My pressure is essentially a ratio. So I could put 740 over 800. Or I can take my volume of 180 and arrange my ratio to where 800 is over 740. Now, the key here is I need a volume smaller than 180. So which of these ways will give me a volume smaller than 180? A smaller numerator will give me a volume less than 180. So I'm going to use my first ratio where 740 is on top. So 180 times 740 divided by 800 is going to be 167 milliliters. So let's look at our next example. In my next example, I have a sample that occupies a volume of 400 milliliters when the temperature is 10 degrees Celsius. Now, remember when we are dealing with gas laws, we have to convert temperature into Kelvin. So 10 degrees Celsius is 283 Kelvin. And if you're not sure where that temperature came from, you need to go back and watch our video on conversion of temperature from degrees Celsius to Kelvin. What must the temperature be in order to make a volume of the gas become 250 milliliters, assuming there is no change in pressure? So pressure is being held constant, and again, my moles of gas is not changing. So this is the relationship between volume and temperature. And this relationship between volume and temperature we call Charles's law. And these are named after the scientists who discovered the relationships. Volume and temperature are going to have a direct relationship, meaning as one goes up, so does the other. As one goes down, so does the other. So they will both increase or both decrease respectively. So let's look at my volume. What happened to my volume? My volume went from 400 to 250, so that is a decrease. So how is that going to affect temperature? It is a direct relationship. So I'm going to see a decrease in temperature. So my temperature was 283 Kelvin. Now I need to arrange this ratio under the volume so where I will get a temperature less than 283. So in order to arrange that, I'm going to have to put the 250 on top and the 400 on bottom. All right. So I am going to do 283 times 250 divided by 400, and that gives me 177 K for Kelvin. Now the problem did not ask you to put it back, temperature back into degrees Celsius. So what I would always suggest is you leave it unless you're asked. So if it said, what must the temperature be changed to in degrees Celsius, then you would convert that out. But since you weren't asked, don't take that extra step. There's no need to do extra work and create yourself an opportunity to make an accidental error by doing extra work that was not required. All right, let's look at number 3. What pressure will a 10-liter sample, so 10 liters of helium measured at 12 degrees Celsius, so that's going to have a temperature of 285 K. Occupy, so we got 12 degrees Celsius, occupy at 36 degrees. So we're changing our temperature to 36 degrees, which is 309 Kelvin. If the initial pressure is 50 kilopascals and volume remains constant. So in this case, we're telling you the size of the sample, but the size doesn't matter because what happens? It tells you volume remains constant. So you got to be careful when you're reading these problems. Don't let extra words get you mixed up. Again, we're not changing the moles of gas. So we're looking at the relationship between pressure and temperature. This is Gay-Lussac's law. All right. And Gay-Lussac's law gives us a direct relationship. It says that pressure and temperature have a direct relationship. So again, as pressure goes up, temperature goes up. As temperature goes down, pressure goes down. All right. So let's look at our temperature. What happened? It went from 285 to 309. So that was an increase in temperature. So since temperature and pressure are directly related, my pressure is also going to go up. That is an increase in pressure. So my pressure is 50 kilopascals. And I have to arrange my ratio such that I get a number larger than 50. So when I look at my ratio, 285 and 309, to get a value larger than 50, my larger number must go on top. My smaller number must go on bottom. So when I plug this into my calculator and solve, I am going to get a pressure of 54.2 kPa. So let's look at another example. I have a closed flask with a pressure of 1.5 atmospheres. And it contains 15 moles of gas. A student uses a syringe to add an additional 5 moles. So if I start with 15 and I add an additional 5, 15 plus 5 means I end up with 20 moles in my final container. And I want the pressure. So volume is not changing and temperature is not changing. This is Avogadro's law. Where Avogadro's law is the relationship between pressure and moles of gas, where N is the mole of gas. So pressure and moles of gas are going to have a direct relationship. Again, meaning as one goes up, the other also goes up. So when I look here at my chart, my mole of gas went from 15 to 20. So I have an increase in the moles of gas. Since it is a direct relationship, I will also find an increase in pressure. So when I set up my ratio here, I need to set it up such that pressure is going to be larger than 1.5. So in order to get a larger value, I need the larger number on top in my ratio. 1.5 times 20 divided by 15 is going to give me 2 atmospheres. All right, let's look at our final example here. A sample of gas occupies a volume of 2 liters. When the temperature is 27 degrees Celsius, so that's 300 Kelvin, and the pressure is 700 millimeters of mercury. All right. What volume will the gas occupy at STP? So what volume? We're looking for volume. Remember, STP is standard temperature and pressure. The standard temperature in Kelvin is 273. My pressure is in a unit of millimeters per mercury. So I need a standard pressure in millimeters of mercury. And if you remember, the standard pressure in millimeters of mercury is 760. So, what is happening? I have not changed my moles of gas, but I have 2 things going on, a change in pressure and a change in temperature. My pressure is going from 700 to 760, so my pressure is increasing. How will pressure affect volume? Pressure and volume are inversely related. So if pressure goes up, volume goes down. My temperature is going from 300 to 273. So my temperature is decreasing. How will a change in temperature affect volume? Temperature and volume, according to Charles's law, is a direct relationship. So a decrease in temperature is a decrease in volume. Now, this is a 2-part problem, my friends. All righties, let us look at our volume. 2 liters. We're going to start with pressure. My pressure is going to create a decrease in volume. So I'm going to arrange these 2 values in my pressure such that 2 liters goes down. So my 700 is on top. I need the smaller number on top in order to decrease 2 liters. Now, this part is simply my effect of pressure on volume. I have a whole nother part, and that is temperature. Now, in this case, temperature is going down, volume is also going to go down. So I need my 2 liters to decrease as well. So when I look at my values here, 273 is going to have to go on top and 300 on bottom. So essentially I have 2 parts. I have the effect of temperature on volume, but I also have the effect of pressure on volume. So I'm seeing here, these are my two parts. So 2 times 700 times 273 divided by my 760 times 300. Put this in your calculator as a single problem. 2 times 700 times 273 in a parenthesis, divided by my denominator, 760 times 300. So make sure you put it in all one problem, use appropriate parentheses. And when you solve for that, you are going to get a volume of 0.168 liters. So this is the way I like to solve gas law problems that involve a change in pressure, temperature, volume, or moles of gas. This particular way works because it really brings out the do I understand what is actually happening. All right, and now that's going to be important because you know there's going to be test questions about your comprehension and your understanding of the material. There is a mathematical equation which you may see in certain textbooks. I don't like that way because what that happens is it becomes a plug and chug, and students don't understand what they're doing or why they're doing it. So we are never going to solve this with a mathematical equation. We will always solve these types of gas law problems using this, what I call the IFE chart, initial final effect, and our ratios.